welcome to this video lecture on constrained finite horizon optimal control. So far we've talked about stability, invariance and Lyapunov stability theory. We've studied finite horizon linear quadratic optimal control problems. We've introduced the concepts of reachability, controllability, stabilizability and observability. And we've used the dynamic programming method both to solve finite horizon problems and to make sense of infinite horizon ones. In this lecture, we will study constrained finite horizon optimal control problems using the dynamic programming method. So consider a discrete time dynamical system, possibly non-linear, which is governed by this equation. Starting from an initial state x0, which is equal to some given state x, and applying a sequence of inputs u boldface n, we obtain a sequence of states x boldface n. The objective is to determine a sequence u boldface n star that minimizes a finite horizon cost function Vn, which is the sum of some stage cost functions plus a terminal cost. The stage and terminal cost functions are assumed to return non-negative values, and xt denotes the state of the system at time t, starting from the initial state x and with the application of the sequence of control actions u boldface n. The minimization of the cost function should be done taking into account certain constraints on the states, the terminal state, and the control actions. Putting it all together, we have this finite horizon constrained optimal control problem. Before we move on, we need a little piece of notation. For two vectors a and b, the notation a is less than or equal b means that a is less than or equal b element-wise. State and input constraints may have the simple form of a rectangle, where, for example, x is between given bounds x-min and x-max. Or we may have more general polyhedral constraints of the form matrix times x is less than or equal vector. We may have integrality constraints, where some variables are allowed to take only finitely many values. This is the case when our system involves switches, or, for example, in a vehicle with a gearbox where we can choose from a finite set of gear positions. More generally, we have a set which is given in this form with some function g, and this can have any geometric shape. As an example, a ball of radius r can clearly be written in this form. Let us now repeat some of the definitions we gave earlier, but this time we will state them in the context of constrained finite horizon optimal control. We say that the sequence u boldface n is admissible for our optimal control problem with initial condition x0 is equal x if it leads to the satisfaction of all constraints along the prediction horizon. The set of all admissible sequences is denoted by big U calligraphic subscript n of x. This is the set of all sequences u boldface n whose elements are drawn from the set u and starting from x retain all future states inside x and steer the terminal state inside xf. The set big U calligraphic n is a set-valued mapping that takes a vector x and returns a set of sequences of control actions. We also define the set of feasible states as the domain of big U calligraphic n. That is, this is the set of all states such that the corresponding set of admissible sequences is non-empty. To put it a little differently, a state x is feasible if we can find at least one sequence of control actions of length n so that all constraints are satisfied. Of course, by construction, xn is a subset of x. We can now write the optimal control problem as the problem of minimizing the cost function Vn subject to the sequence of control actions u boldface n being admissible. The problem is feasible for all x that are inside the set xn. The value function of this problem is defined to be the minimum of the cost function subject to the constraints, provided of course that this minimum exists. This is denoted by Vn star. As we've discussed earlier, we cannot assume that the minimum is attained, even in the convex case, unless we impose appropriate conditions. More on that later. Next, we define the solution mapping of the problem to be the set of minimizers. This is a set-valid mapping. Indeed, for some given state x, we may have multiple minimizers, or we may have none. The solution mapping is denoted by u calligraphic n star of x. Overall, we have a parametric optimization problem where the cost function and the constraints depend on the initial condition x. Previously, we studied finite-horizon linear quadratic optimal control problems of the form shown here, and we said that these are problems with a convex quadratic cost function and linear constraints. The set of state constraints is the entire Rn. The set of terminal constraints is Rn again, and the set of input constraints is the entire Rm. Moreover, the minimum is attained, all sequences of inputs are admissible, and all initial states are feasible. We can solve this problem by using the dynamic programming approach, and we can find a linear control law kappa n star. If we add constraints to this problem, we may not be able to solve it and obtain an explicit solution. A notable exception is the case where x, xf, and u are polyhedral. In that special case, we can compute kappa n star and Vn star explicitly, and kappa n star is piecewise affine over a polyhedral partition of the set of feasible states. However, in most cases, an explicit solution is not available, and we need to resort to some numerical method and appropriate software to solve such constrained optimal control problems. We will now state 4 rather weak conditions that should be satisfied for the problem to be considered sufficiently regular. These are that, first of all, the state and terminal cost functions are continuous functions. The system dynamics f is a continuous function. The sets of constraints x, xf, and u are closed, and either u is a compact set or L is above a k-infinity class function of the norm of u. In other words, the growth of L is controlled by the norm of u. If these conditions are satisfied, then for all feasible states x, the minimum of the constrained optimal control problem is attained. This means that the value function Vn star is defined for all feasible states x, and the solution mapping is well defined and non-empty for all feasible states x. So here is what we're gonna do next. We will cast the constrained finite horizon problems as unconstrained finite horizon problems. And this will allow us to apply the dynamic programming method exactly the same way as before. To that end, we need to define the set of extended real numbers. The set of extended reals is the set of real numbers with the element plus infinity. We will later define costs that can take the value infinity. An infinite cost will be associated with the violation of a constraint. A function that returns an extended real is called an extended real valid function, or ERVF for short. The domain of such a function is the set of x where the function is not equal to infinity. Given a set A, we define its indicator function, denoted by delta subscript A, to be an extended real valued function which is equal to 0 if we are inside A and plus infinity if we are outside of it. This is an extended real valued function with domain the set A. The idea is that instead of imposing the constraint x is inside x, we can use the cost function delta x. So for example, take this optimization problem. Minimize f subject to x is in A. This can be written equivalently as minimize f plus the indicator function of A and without any additional constraints. By defining the extended real valued function f bar, which is equal to f plus the indicator function of A, we see that the original problem is written as minimize f bar. And this has the same form as the non-constrained optimization problem. Let's see how we can apply this trick to constrained optimal control problems. Here we have the state and input constraints at each time t, and the terminal constraints on the terminal state xn. These can be moved to the cost function by using indicator functions. The constraints xt in x and ut in u are captured by adding the indicator of the Cartesian product of x cross u into the cost function. And the constraints on the terminal state are encoded by the indicator of xf. Let us now denote these two functions by L bar and Vf bar. We define L bar to be L plus the indicator of x cross u, and Vf bar is Vf plus the indicator of xf. In the end, we have written the original problem in the form of an unconstrained optimal control problem, the key difference being that the stage cost function and the terminal cost function are extended real valued functions. Now, the good news is that the nested optimization principle holds for extended real valued functions, and this means that we can apply the dynamic programming method exactly as we did previously to the case of constrained problems. So let's see how this works. We start by writing the definition of Vn star, which is the minimum of the cost function, here an extended real valued function, and it is subject to the system dynamics and the initial condition. Then we split the minimization into two parts in order to use the nested optimization principle. In particular, we minimize with respect to the last control action, un-1. We do that separately, and we see that this part of the cost depends on un-1, but this one doesn't. This allows us to move the minimum with respect to un-1 inside the brackets and substitute xn equals f of xn-1 and un-1. This quantity is precisely v1 star of xn-1, and it is an extended real valued function. The problem now is written like this. We see that it has the same form as the original problem, but with a shorter prediction horizon, n-1, and a different terminal cost, v1 star. Note that v1 star of x is the value function of the optimal control problem with horizon 1 and initial condition x. We have defined v1 star to be the minimum with respect to u of L bar plus vf bar of f of x, u. We can follow the exact same procedure, starting with the problem with horizon n-1 and terminal cost v1 star, and we can follow the exact same steps to obtain a problem of the same form as the original one, but with a prediction horizon n-2 and the terminal cost v2 star. v2 star is the value function of p2, the optimal control problem with horizon 2. And same as in the unconstrained case, Vt plus 1 star is determined from Vt star, with V0 star being the terminal cost Vf bar. We can also define eucalligraphic T star to be the corresponding set of minimizers. And a control law kappa T plus 1 star is any selection from this set. Moreover, if we plug kappa T plus 1 star back into the first equation, we obtain this characterization of Vt plus 1 star. And this is all the same as in the unconstrained case. The key difference is that all functions vt star are extended real valid functions. Under the regularity assumptions, the domain of vt star is equal to the domain of eucalligraphic t star. We then define the set x0, which is the domain of v0 star, which is the same as the domain of vf bar, which is the set xf. And then x1 is the domain of v1 star. I will leave it to you to confirm that the domain of v1 star is equal to all states in x for which there is a control action taken from u, such that the next state, f of x, u, is inside x0. Recursively, we have that xt plus 1 is the set of all states in x for which there is an input u taken from the set big U, such that f of x, u is inside the set xt. In other words, xt plus 1 is the set of states that we can move into xt in one step without violating any constraints. And xt is the set of states that we can steer to x0 in t steps without violating any constraints. The definition of xt allows us to write the dynamic programming recursion in an alternative way without using extended real valid functions. We update a sequence of sets where xt plus 1 is the set of states in x for which there is a control action u in big U, such that the next state f of x, u is inside the set xt. Then vt plus 1 star is the minimum over all u inside the set u, the minimum of L of x, u plus vt star of f of x, u, subject to the constraint f of x, u is inside xt. Function vt plus 1 star is defined for all those states x inside xt plus 1. And we initialize these sequences with x0 is xf and v0 is vf defined for x in x0. At the same time, eucalligraphic t plus 1 star is the corresponding set of minimizers, and under the regularity assumptions, its domain is equal to xt plus 1. We also have the control laws kappa t plus 1 star, which are a selection from the set eucalligraphic t plus 1 star. Lastly, we have Bellman's principle of optimality. Suppose we have solved the optimal control problem with horizon n, and we have obtained an optimal policy consisting of the control laws kappa n star, kappa n minus 1 star, and so on up to kappa 1 star. Then, for any j between 1 and n, the truncated policy from kappa j star to kappa 1 star is optimal for the problem with horizon j. This means that when we solve an optimal control problem with the DP method, we solve all problems with horizons from 1 to n. So this much about constrained finite horizon optimal control problems. Thank you very much for watching, and I'll see you next time.